So let's start by seeing what is a linear first order equation. Now remember that first order simply refers to the derivative that we're talking about. This particular one, you see we have a first derivative, hence it's a first order equation. Now linear does have some connotations to what we learned back in algebra. We learned a linear equation was one where we could write y equals something times x plus something else. That was a linear equation. We could say it a number of ways. Ax plus by equals some constant. But there were no exponents involving the variables. Well, in here, our variables are y, since that's what we're trying to solve for, and the derivative of y. So basically, it's linear if we have no powers of y or the derivative, no radicals of y or the derivative, and no functions of y or its derivative. So that's the idea of linear first order. Let me show you some examples of linear first order. If we take this differential equation, we can modify this to look like the standard form that you see up above by moving the x cubed to the other side and dividing through by x. We get this standard form for a first order linear equation. The quantity on the right is what we're referring to as the function f. The function, the stuff beside the y, is what we're calling p. We'll have more to say about that later. Anyway, now we'll do a little algebra to this by multiplying it out. Move the term without the y to the other side. Divide through by the x squared on the front of the dy dx. And we have our standard form. Now this is not a proof, but an explanation for the technique that we use for solving these first order linear equations. Now as you can see here, it comes from the product rule. Now I'm going to create this new function that I'm calling by the Greek letter mu, because that's what your textbook author uses. And according to the product rule, the derivative of some function mu and some function y comes out to be what you see over here. Now, if we take the standard form and multiply through by the quantity mu, you notice that these look an awful lot alike. In fact, they would be the same if the derivative of mu with respect to x was the same as mu times p. And that's kind of the emphasis behind our technique. So, in order for the derivative of mu times y to be equal to mu times f, the derivative of mu with respect to x has to be mu times p. Now, I'll see just in a minute how this works into the technique. Now, if we take the integral of both sides of this, the integral of the derivative of u times y is u times y. And we can solve for y just by dividing both sides by mu. So that's kind of the idea. And again, this is all fine and dandy as long as this is true. So that's kind of our technique. We want to find the mu that makes this true. So what we're going to do is separate this. It's separable into 1 over mu d mu and p times dx. Integrate both sides, and we get the ln of mu plus some constant equals the integral of p dx, which we don't know because we don't know what p is. However, the constant can be anything because, again, what we're trying to do is to find something that works for mu. And so c can be anything whatsoever. I think I'll choose c to be a 0. And we can finish solving this by doing the natural exponential of both sides. Remember, the absolute value gives us plus or minus. But again, just like we mentioned, what we're trying to find is just some mu that will work. We don't care if it's the plus or the minus, so we'll choose the plus. So this is the key to the technique. We find what's called the integrating factor, which is designated by mu, by doing e to the integral of p times dx. Now here's how that works. Now I'll go through these steps with you with a few examples to show you how we use the technique. We begin by writing this differential equation in standard form, partly to verify that it is indeed a linear first order equation. For this one, it just means adding x cubed to both sides and then dividing through by the x. Now, the p referred to in the standard form is the 4 over x, and the f is x squared. We don't particularly need the f right now. However, we need to find the integrating factor by doing e to the integral of the 4 over x. So let's integrate the 4 over x, and then let's do e to that power. Well, now e to the exponent of ln of x to the 4 comes out to be just the x to the 4. So that's our integrating factor. Now here's how that works. We simply change our differential equation into this. We're going to have the mu times y, which is x to the 4 times y, and the integral of mu times f, which is x to the 4 times x squared. Now we actually need to do that integral. That integral on the right hand side at this point should be something that we can do the integral of. The integral of x to the 6, of course, would be x to the 7 over 7, and we can solve for y by dividing by x to the 4. Now that's how the technique works for linear first order equations. Let's change this one into standard form. All we need to do is move the 3e to the xy over to the left and divide through by e to the x. Here, the p that we use for finding our integrating factor is the -3. And so we have e to the integral of -3, which would be e to the -3x. So now we write the differential equation in this form. Mu times y equals the integral of mu times f, and finish it out by actually performing the integral. So over on the right hand side, we need to do that integral. We'll multiply it out and then do our integral. We may have to do a substitution or something to integrate that. To finish solving for y, we multiply both sides by e to the 3x, or divide by e to the -3x. and we have our general solution. Here's my last example. This is already in standard form. We just recognize what the P is, the cotan of x, by changing that up just a little bit. Comes out to be cosine of x over sine of x, which we can do the integral of by substitution. Let u be the sine of x, du is cosine of x dx, so we end up with e to the ln of the sine of x as our integrating factor. So now we change our integral. Mu times y equals the integral of mu times f of x. And finish it out by doing the integral on the right-hand side and solve for y.